Hello everyone, welcome to Math 120, section 5.1. Today we're going to start off with some definitions. First, every whole number greater than 1 can be classified as either prime or composite. So let's talk about the difference. Prime numbers are divisible by only 1 and themselves. If a number is prime, it is only divisible by 1 and itself. Prime numbers are always bigger than 1, though. Remember, they got to be bigger than 1. Composite numbers are numbers that are not prime. That means they're divisible by something other than 1 and themselves. And then I put a little note here. The number 1 is neither prime nor composite, but is instead called a unit. Think of what's the smallest increment you can increase something by in whole numbers? That's 1, right? You're moving 1 unit up. So we call it a unit. It's the base building block of the numbers. Now, we have a little table here for divisibility rules. When looking at a number, determining whether it's divisible by another number can be a little tricky. We've got some examples here. 2, 3, 4, 5, 6, 8, 9, and 10. So we're going to check to see whether a number is divisible by them, and we'll walk through the test as we go through. So the number in question is 563,244. So and the possibilities are 2, 3, 4, 5, 6, 8, 9, or 10. We want to check each of these to see if they work. So let's take a look. Which ones work? 2. Is this number here divisible by 2? Well, the test is even. Is this even? Yes. So it is divisible by 2. How about 3? The sum of the digits of the number is divisible by 3. So let's do some scratch work. 5 plus 6 plus 3 plus 2 plus 4 plus 4. I got to add these up. I get 11, 14, 16, 20, 24, right? When I add the digits up, I get 24. So the sum of the digits is divisible by 3. Is 24 divisible by 3? Yes. So that means this number, 563,244, is divisible by 3 as well. How about 4? It says the number formed by the last 2 digits is divisible by 4. So once again, let's do some scratch work over here. What are the last 2 digits? 44. Does 44 divide by 4? Yes. So we've, been batting 1,000 so far. We've got 1, 2, 3 that do work. How about 5 though? Is this divisible by 5? The number ends in 5 or 0. Nope. So no, it is not divisible by 5. How about 6? The number is divisible by 2 and 3. Yes, yes. So that makes this one yes. It is divisible by both 2 and 3. Next, we skip 7. We move on to 8. The number formed by the last 3 digits is divisible by 8. So once again, we're going to put a little scratch work here. The last 3 digits are 244. And now you might want to ask yourself, is 244 divisible by 8? If we paused and think about it for a little bit, we'd find out that no, 244 is not divisible by 8. That means 563,244 is also not divisible by 8. Now, number 9, the sum of the digits is divisible by 9. I already summed the digits when I was checking 3. So is 24 divisible by 9? Nah. So that's a no as well. And then I move on to 10. The number ends in 0. That's not a 0, so no. So, determine whether 563,244 is divisible by any of the numbers in the table above. It's divisible by 2, 3, 4, 6, and that's it. So we checked each one. These will help save us some time when we talk about the next topic, and that's prime factorization. It will be a lot quicker for us if we're able to quickly determine if certain numbers divide other numbers. So prime factorization, what is that? Prime factorization is the breakdown of a whole number into all of its prime divisors. Divisors is the same as factors, right? If something is a divisor, it's also a factor of that number. So how do we find the prime factorization? Well, the way I like to do it is write the number out and then start checking which numbers can divide it, working through the prime numbers. What's the first prime number? The number 2. Can 2 divide 1,500? Yeah, it's even. So I'm going to put 2 here, and then I'm going to put 750 here, because 1,500 divided by 2 is 750. Now I'm going to continue this process of breaking the number down each step by something that divides it. 750. Does that divide by 2? Yes. So I have 2 here, because 750 divided by 2 is 375. So I divided by 2, divided by 2. Next, 375. Does that divide by 2? It doesn't. So I'll skip. What's the next prime number? 3. I'll check 3. Does 3 go into 375? Well, our divisibility says, do the digits add up to something divisible by 3? 3 plus 7 is 10, and 5 more is 15. 15 does divide by 3, so 3 also divides 375. What does it give us when we divide? 3 into 375 gives 125. Now, I'm going to check 3 again, right? I've moved on to 3. Does 3 go into 125? Turns out it doesn't, right? If you try the trick, these add up to 8. 8 is not divisible by 3, so I can't divide 3, right? We'll move on to the next prime number. What is the next prime number after 3? It's 5. Does 5 go into 125? Yeah. It ends in 5, right? 125 divided by 5 is 25. And then, lastly, does 5 divide 25? Yes, it does. And I'm left with 5. Notice I broke my number down until it became a prime number. I can't break 5 down any farther. Nothing goes into 5 except itself and 1. So, I have found the prime factorization. 1,500 is equal to 2 times 2 times 3 times 5 times 5 times 5. 2, 2, 3, 5, 5, 5. 2, 2, 3, 5, 5, 5. Or, if we wanted to use some exponents, we're welcome to do that as well. We can have 2 to the second times 3 times 5 to the third. We broke 1,500 down into all of its prime divisors. We factored it into its prime factors. We found its prime factorization. And that is the process we will use. We keep breaking the number down until it cannot be broken down any farther. Now, where will we be using this? How will we be using this? Well, we want to find GCFs and LCMs. GCFs are greatest common factors, sometimes called GCDs for divisors, and LCMs are least common multiples. So let's define these. The GCF of a list of numbers, the GCF of a list of numbers is the largest number that evenly divides all numbers in the list. The GCF is the largest number that evenly divides all numbers in the list. Whereas the least common multiple, the LCM of a list of numbers, is the smallest number that can be evenly divided by all numbers in the list. So we have a GCF and an LCM. The GCF is the largest number that divides everything in the list. The LCM is the smallest number that can be evenly divided by everything in the list. So let's find them. Let's see what it looks like to find GCF and LCM. So, finding the GCF. So, to find the GCF, we find the prime factorization of each number. We list the prime factors that appear in all of the prime factorizations, and then we multiply the list from step 2 together. So, we got to find the prime factorizations. So, let's break 36 down. It divides by 2 to give me 18, which divides by 2 to give me 9, which divides by 3 to give me 3. So 36 equals 2 times 2 times 3 times 3, right? 2, 2, 3, 3. And then 90 divides by 2 to give me 45. 2 doesn't work anymore. I got to move on to the next one. 3 to give me 15. 3 again to leave me with 5. As I divide each line, 90 divided by 2, 45. 45 by 3 is 15. 15 by 3 is 5. And so 90 is equal to 2 times 3 times 3 times 5. So I found the prime factorization. I listed the prime factors that appear in all of the prime factorizations. Which ones do they have in common? Well, for my answer, for my GCF, I'm going to find the ones in common. They both have a 2. Do they both have a second 2? No. This one has a 2, this one doesn't. They both have a 3, though. And they both have a second 3. So my answer will list each of those. A 2, a 3, and a 3. Those are the ones that were in common. They appeared in both, right? They appeared in all of them. So these are the ones that were in common. Greatest common factor, right? Multiply these together. 2 times 3 times 3. 6 times 3 is 18. So 18 is the largest number that divides 36 and 90. And if you ran through and checked, you'd find that that's true. We didn't have to check all the numbers, though. We just had to follow the process. Now, 36 and 90, you might have been able to see that 18 works for those numbers. It might have jumped off the page at you. Sometimes, if you're comfortable with your division rules, you might notice GCFs before you start working the problems out. However, 315 and 450, little bit trickier, little bit harder to figure out what's going on. So, let's divide these. 315. Is this divisible by 2? No. So I'll jump to the next prime number of 3, because it is divisible by 3 to leave me with 105, which is also divisible by 3, right? To leave me with what? 35, which is also divisible by, it's not divisible by 3, it's divisible by 5, to leave me with 7. So 315 equals 3 times 3 times 5 times 7. And then 450, that's divisible by 2, 225, which is not divisible by 2, but it is divisible by 3, right? So I'll divide by 3 to give me 75, which is divisible by 3, because 25 times 3 is 75, which is divisible by 5 to leave me with 5. So 450 is equal to 2 times 3 times 3 times 5 times 5. So which ones do they have in common? Well, they've got 1 3 each, a second 3 each, a 5 each, and then this has an extra 7, and this has an extra 2 and an extra 5, but those are not shared. They're not in common, so I won't use them. I don't need them. So the GCF is equal to 3 times 3 times 5. I take the ones I circled. 3 times 3 times 5 is 45. 45 is the GCF of these two numbers. 315, 450, 45 is the largest divisor of both of those. And notice it was the same process. I didn't switch any of my techniques. Just because I was working with bigger numbers does not mean I switched the technique. Good. So, finding the LCM. Finding the LCM is a little bit different. It's a little bit trickier. It can trip us up a little more easily. So finding the LCM, rather than write out the technique first and then do it, I wanted to walk through the technique out loud. So, the LCM. The first step is find the prime factorizations. We're going to find the prime factorizations, which we already did. 36 was 2233, 2 times 2 times 3 times 3, and 90 was 2 times 3 times 3 times 5. We already found them in this step, right? No reason to do them again. Now that we've found them, we take the largest amount of each factor. And the reason I wanted to walk through this rather than show the technique off first is because this is the weird part. For the LCM, they don't have to have the same number of them. They just have to have the number. So first, which prime numbers are here? Well, I have 2, 3, and 5, right? I see some 2s, some 3s, and 5s. Which number has more 2s? The first or the second? The first one does. So I'm going to take those 2s. It's the larger amount of 2s. I'm going to take those 2s. Now, how about moving on to the next prime number? Which has more 3s, the first or the second? They have the same number, so it doesn't matter which one I choose. I'm going to choose this group of 3s just because I like the number 90 more. So they both had the same number of 3s, so it didn't matter which one I picked. What's the next prime number that appears? 5. Which has more 5s? Well, this one does, right? That one has more 5s. So I take the largest occurrence of each prime factor. I take the largest appearance. I take the largest amount I can get. I'm always trying to get as many as I can for the LCM. And that's a little bit weird, right? They don't have to have the same number of them like they did for the GCF. They have to pair up. They have the largest occurrence. And then these become my answer. 2 times 2 times 3 times 3 times 5. 2 times 2 is 4, times 3 is 12, times 3 is 36, times 5 is 180. And so the largest common multiple is 180. Does 36 divide 180? Yep. Does 90 divide 180? Yep. And 180 is the smallest number that is true for. There's no number smaller than 180 that you can divide by both 36 and 90. So let's take a look at it again. Let's do it for 315 and 450. Once again, we'd find the prime factors first, but we already did it up here. 3 times 3 times 5 times 7. And 2 times 3 times 3 times 5 times 5. Which prime numbers are here? I have 2, 3, 5, and 7. So, let's start with 2. Which number has more 2's? This one. Let's move on to 3. Which has more 3's? They've got the same amount. I'm going to take these ones. It doesn't matter if I took these ones or these ones, because they have the same amount. Next, we move on to 5's. This one has more 5's. Then lastly, we move on to 7's. This one has more 7's. So for my answer, the LCM is equal to 2 times 3 times 3 times 5 times 5 times 7. I take the numbers I circled, just like I did before. Now, I need to multiply these out. 2 times 3 is 6, times 3 is 18, times 5 is 90, times 5 is 450, times 7, 450 times 7 would be 280, 3150. I think it's 3150. Let's double check with the calculator. 2 times 3 times 3 times 5 times 5 times 7. 3150. Always good to use technology to confirm what we thought. So 3,150 is divisible by these two numbers, and it's the smallest number that is true for. Notice this technique, a little bit different, right? But the same first steps. That's why they're on the same page. I wanted to make sure I could point out the similarities and the differences. The similarities are you need to find the prime factors for both techniques. The differences are, for the GCF, you're circling the pairs that are in common and multiplying them. Notice we got smaller numbers than we started with. Should make sense. They're divisors, they're factors. They should be smaller. Then for LCM, we took the largest occurrences. Notice we got bigger numbers than we started with, which once again should make sense. We're looking for a multiple. It should be larger than what we started with. So that's GCFs and LCMs. And that brings us to the end of section 5.1. Thank you for joining me, and I will see you next time.